So I volunteered to go first, but they didn't tell me that I'm a warm-up for the astronaut. So, okay. I'm going to present you my research. It is about the evolution of Mars' early atmosphere and climate. I'm from the Weizmann Institute of Science, which is a science university, I think one of the top 10 in the world, but it's in Israel. And many people ask me, what is geology? So, yeah, geology is a rocket science. And first thing is just a bit of comparison. I would like you to see the differences between Earth and Mars. In my presentation, I keep text to the minimum, and in the title, it's written the take-home message. So the distance from Sun is about 1.5 farther away for Mars, which means the Sun is smaller in the sky, so less radiation penetrate the surface. The axial tilt, though, is almost the same, which means that seasons, summer, winter, on Mars is almost the same as on Earth. The problem is the year is 2 times longer, but the day, though, almost the same, 24.7 hours day, not day, like day. Gravity, as you can see, Mars is much smaller, which means it affects gravity, but the land area is almost the same because most of our surface is water. Mars don't have oceans, so basically the same land area. But, and this is the big issue, this is what we are talking about, the atmospheric pressure on Mars is only 0.6 that on Earth, which means for any practical use means we have almost no atmosphere on Mars. So you can see the thin atmosphere. It composed mostly of CO2, 95%, a bit of nitrogen, argon, almost none of oxygen and other gas. The thing is, again, the pressure is 0.6% of what we have on Earth, which means, if you remember Jeff Hoffman in his lecture, he talked about the triple point. Triple point is how the water phase diagram changes between the phase in comparison to the pressure and temperature. So on Earth we get 1 bar, 1 atmosphere of pressure, and it gives us 273 Kelvin, 273 degrees Kelvin for melting of water, and boiling water 373 Kelvin. But on Mars, as we said, the pressure is very low. It's exactly on the triple point. And what that it means, and this is the big issue, liquid water are unstable at the present day Martian surface. Okay? The phase liquid is unstable, and solid water, which is ice, can transform immediately and to evaporate into gas. So, what is the conflict? Maybe you know, maybe you don't know. Google Earth can turn into Google Mars. So you just press on the button where I showed you and you get Mars. So I'll take you to a small tour, just to get a specific understanding. You can see that those areas are heavily cratered, which means they are older. They had more time to get hit by meteorites. And newer areas has almost no craters. But the thing is, why I opened Google Maps for you, is in order to ask you, what do you see now? What's weird about the surface? Can anyone answer? Yes?
Well, it looks like some kind of flow.
Okay, there is lines here, and if you look here, it's even, yeah, you can see that there is geomorphological features that resembles fluid on Earth, maybe like in a desert. Okay, I thought you would not agree with me, so I planned another one. This one, for example, looks almost like back in my home. Okay, there's a great drainage basins, which probably most of you agree with me that it's probably a flow of water. Now, what was the conflict? You remember, no phase of liquid water can be stable for a long time on Mars' surface. But we see on the old surface, the one that heavily cratered, the old surface covered with the geomorphological features of liquid water that flowed on the surface. So we have a conflict. Most scientists think that in early days, Mars had different atmosphere and then different climate. This is why we can explain the geomorphological features while we don't have pressure. And then they thought, what made the change? And there are a couple of theories. I'll go through the most important. Dr. Grimm, in his lecture, talked about the solar wind. In Earth, we are protected, but Mars, early in his early life, the magnetic field turned off and the solar wind stripping turned on, and it depleted part of its atmosphere. Another mechanism is the ejection of the atmosphere from impacts of meteorites. When a meteorite hits, it ejects everything, solid, liquid, and gas, and it can go, the velocity can be as much as to engineers, you have names, but enough to leave the gravity of Mars, okay? And the last thing, the last theory, and here well geologists go in, is sequestration of CO2 by mineral carbonations. What is mineral carbonations? Carbonations, a water-mediated replacement of silicate mineral by carbonates. Basically, it means that you take a rock, solid rock, volcanic for example, basalt. You take rain, you take CO2 from the atmosphere, you combine it all, and you weather, you erode the basalt into a different form. For example, clays, secondary minerals. There was supposed to be an equation here, but you can see I tried to do it more popular science. Basalt, water, and CO2, it's the atmosphere and the rock combined together, and with the conservation of mass, you get clays and carbonate minerals. This mineral, for example, is calcite, calcium carbonate, and this is a kind of carbonate mineral. So, here's the thing. Again, we don't have atmospheric pressure now, but we have geomorphological features for early days, fluid of liquid water on Mars. Scientists think that part of the atmosphere went into the rock. Now, most of the of Mars' surface covered in basalt, and you would expect that we get a big slab of carbonates all over the planet. But in the end, when scientists went and checked, they realized not many carbonates are there. First time we found carbonates is on meteorites that came to Earth from Mars. We found 1% of carbonated water. It was like a big achievement. Later on, remote sensing of the satellite people here. We have 5 missions that are now circling Mars, and they detected a couple of small locations of carbonates. Again, less than we expected. And last but not least is the rovers, which actually gave us the best result. They found great carbonates, but again, in small amount. And this is the problem. We thought we'll find a lot of carbonate, and it will explain why we have no atmosphere on Mars now, but we didn't find it. Okay? And here I come into the picture. We thought, where could possibly carbonates formed in a way that we cannot detect them? So my advisor thought on specific environments, and I go briefly, it's just the means if it will be as an ocean, open surface, connect to atmosphere, or beneath surface with no connection to atmosphere, you will get different carbonate, okay? For a specific environment, there's a specific carbonate formation. But I chose to tell you just about this one. I walked a lot about this. Basically, it's a desert. It means you get rain, it's precipitated on the earth, on the soil, but it cannot be saturated, not enough water in the soil, and very fast it evaporates. So I started to simulate it in the lab. I took some calcite, I dissolved it in water with CO2 of 1 atmosphere, no oxygen. I took a test tube and dropped some drops inside. This is the substrate. It's a glass bit. It's glass bit. It's as if it is soil. And as you can see, drop by drop, I iterate and made a wetting front and stopped for 2 months, just creating this wetting front. After that, cemented it with polymer, with an epoxy, and this is how it looks. Cut it with a diamond saw and took it to all kind of instruments. For example, scanning electron microscope. Those are the glass bits, and you can see it's a scale of microns, remember. You can see that on the glass bits we get those specific minerals, which I thought they are the carbonates, right? So there's a specific instrument that can tell you what's inside, and you can see that the blue, which is calcium, follows pretty good where the specific minerals, the specific crystals are, and probably those are the carbonates, right? Another mechanism, another instrument is a micro CT, like CT they do on your body, but micro CT for small objects. So you get the beads, we erase the beads, and only what that remained on the surface colored with blue. It was another way for us to understand how the sediments form on the glass bead. And what's next? I need to take it to an instrument that can check the isotopes. If I know what the isotopes inside the carbonate, I can make an identity card for this specific environment. So if a rover finds carbonate on Mars and it measures it, okay, you can see that it's the specific isotope and it's exactly like mine, and I know how I created it, so I can tell him how it created on Mars. Like in the ISU, I work in 3 stages. That was the first, work in a lab. The second is go to the field. I'm thinking about going to Yucca Desert. There's lots of carbonates there. This is the carbonate, and see if it works for me. Maybe even the Dead Sea, it's much closer. You can see lots of carbonates in the Dead Sea. And we had a new thought, Idris thought about it, going to a mock mission like we have in Hawaii, and try my research, his thought about his research, try to combine it and do something in a mock mission on Hawaii. And the last part will be to go to Mars, or not, but to try if my simulation actually works, to take from NASA or from whoever put a rover on Mars, give them my identity card and see if it matches. Yeah. Questions? Yes, Helen.
The sedimentation process will be different on Mars because of gravity.
Because of what?
Difference in gravity from Mars to Earth, with different size particles.
No, okay. I tried not to go into details. Usually I give the lectures to people from my field, so I did it really like a popular science. There is so many things you can change. You can change the pressure, the temperature, the solute you can change everything, you will get different outcomes. So we tried something simple. We can change the grain size, we can change gravity, I don't know, and we'll get something else. But for now, it's just basically an identity card. Yeah. Yes.
With the available data from the rovers of NASA, can you do the inverse process?
We can. People done that, and it gives different results. You can do models, simulations in a computer. I try to do something else because it's the front now. Okay, everybody talks about it. I try to come from a different approach. Everybody do the models. I try to, as a geologist, try to be a geologist and work with something, with solid. So yeah, we can talk about it later. I can explain you how they do it.
Yeah, Roy, I can assure you, a safe return if you do some simulations on the moon first. We'll happily bring you back, but we can't assure you a return if you go there.
Right. By the way, the moon is a completely different story. We don't see the geomorphological features on the moon and no atmosphere, and yeah, it's a completely different story. More questions? Yes.
Do you also know a bit about the geology of other planets, or your specialization is really Mars?
You need to choose one thing when you do your thesis, right? So I chose that. Maybe someone will offer me, I don't know, to do a PhD in his university and it will be on another planet. By the way, the Weizmann Institute, the university where I do my thesis, is a great university. And I thought not many people would come, so I thought to bring you presents so each and everyone can take with him because you came to hear my lecture. So after the next lecture, each and everyone can grab one thing. There is brochures in English, German, Italian, Spanish, and French. Because, no, if you read about it, it's a great university, and if someone thinks about it, not just from science, we have engineers, and we have people from all fields, but in the end, it's a science university. So, feel free. Am I on time?
It's okay, so give a big applause.